today. So, in the last lecture we were discussing about stop and wait protocol. We have seen what it is. It is really a simple kind of protocol which is used both for error control as well as for flow control in some case. But since this is a simple protocol, we will look at its performance now. So, we will first finish our discussion on this stop and wait protocol, and this we have already seen. So, each the sender station sends one packet which are ACT. If it comes with some error, it may send a negative acknowledgement. It may not arrive at all. In that case the sender will time out. In either case, that means when it is getting a negative acknowledgement or whether it is getting a timeout, it will retransmit that frame, retransmit whichever frame was just transmitted earlier. And the point to note is that there is only one frame which is in transit in the channel at any point of time, whether it is the frame or the acknowledgement or the negative acknowledgement. So, this is the stop and wait ARQ, which we have automatic repeat request. We have already discussed this, and we have seen that the main advantage of stop and wait ARQ is its simplicity, and the disadvantage is that it is highly inefficient use of communication links. So, what is the efficiency we will see. By the way, this protocol sometimes is also known as alternate bit protocol. It is called alternate bit because one person sends with a bit 0, the other person makes it 1 and sends it back. So, this way 1 and 0 alternates, so that you know that when you send when you have sent an acknowledgement, which acknowledgement it is, etc. Okay. Now, let us look at link utilization in stop and wait. So, how much we are utilizing the link? With the use of multiple frames for a single message, the stop and wait protocol does not perform well. Only one frame at a time can be in transit. So, let us illustrate this with an example. Suppose the transmission time, that is the time it takes for a station to transmit a frame, this is an important parameter. Let us normalize it for the time being, this to a value of 1. By transmission time, we mean that the sender from the time it takes from the when it starts sending the first bit of the frame up to the time it takes to transmit the last bit of the frame. So, this depends on the rate at which the sender is pushing the frame into the channel. All right. So, we will normalize, take it as a normalized value of 1, and then that is one component of the time. The other component is the propagation delay. This is the time it takes for a bit to travel from the sender to the receiver, because there will always be a finite propagation delay, because depending on how long the channel is, depending on maybe the distance, depending on the speed at which the signal travels, etc. There will be a propagation delay, the time it takes for the first or any bit to move from the source to the destination. So, let us call this A. Now, if A is less than 1, which means that what? That means that the remember that we have normalized our transmission time to 1, which means that the first bit of the frame has already reached the receiver when some of the later bits are all being sent by the sender. So, the frame is sufficiently long such that the first bits of the frame arrive at the destination before the source has completed transmission of the frame, and if A is greater than 1, that means the sender completes transmission of the entire frame before leading bits of the frame arrive at the receiver. Of course, the sender now has to wait for the acknowledgement to arrive. So, of this time only the T frame is actually spent transmitting data, and the other time they are idle. So, therefore, the efficiency of the utilization is T frame divided by Td, which is the total time, and Td has got two components. One is this T frame, time to send the frame, transmission time, plus twice the propagation time. Why twice? Because the signal or the message has to the frame has to reach the destination, and the destination has to send an acknowledgement back. So, one T prop this way, one T prop that way, that is twice T prop. So, that is the efficiency. Now, if we define A is equal to T prop by T frame, which means that if a equal to 1, we have the propagation time is equal to the time frame. So, it just fits, all right. Anyway, so if this is that, so u is equal to 1 plus 2a. If you look at the previous formula, so if you divide the numerator and denominator by t frame, so we get 1 from here, 1 here, and t prop by t frame, that is our ta. So, a. So, this is 1, u is equal to 1 plus 2a. So, this is the efficiency. Let us just see an example with some numbers. A channel has a bit rate of 4 kbps and a propagation delay of 20 milliseconds. For what range of frame size does the stop and wait protocol give an efficiency of 50%? Okay. So, we want to achieve an efficiency of 50%. My channel has a bit rate of 4 kbps. That means, this is the rate at which you are pumping in data into the channel. This is the maximum rate which the channel can carry, and it has got a propagation delay of 20 milliseconds. So, I want to find the optimum frame size to get a 50% for getting 50% efficiency. So, r, the rate is 4 kbps, t prop is 20 milliseconds. We want to find L, that is the length of the frame. So, u is equal to t frame by t frame plus 2 into t prop. We want u, that is efficiency, to be 0.5. So, 0.5 is equal to this. So, t frame is equal to twice t prop is equal to 2 into 20 milliseconds, which is 40 milliseconds. So, t frame better be 40 milliseconds, because this is 2 into 20, t prop is 20. So, 2 into 20, 40 milliseconds. So, if this is 40 milliseconds, then we will get a value of 0.5 on this side. So, length of the frame is equal to r, that is the rate at which we are sort of pumping in into t frame, which is 4 into 10 to the power 3 into 40, and this 40 is in milliseconds. So, into 10 to the power minus 3. This all this 10 to the power 3 minus 3 cancels. So, we get 160. So, 160 bits. Thus, for frame sizes L is equal to 160 bits, the stop and wait protocol gives an efficiency of 50%. Okay. Please note that I mean, you will not be able to better this. That means, if it is L equal to 160 bits, then your T frame is equal to this 40 milliseconds, which is twice the T prop. Okay. Now, we come to the topic of flow control. If you remember that our data link layer had these several functionalities, chief functionalities, and one of them was framing, which we have discussed. Then there was the error control, and sort of associated with error control, or somewhat closely linked with error control, we have the flow control. So, the flow control is the other functionality. So, we will see how flow control is achieved, some schemes for that. So, flow control is a technique for assuring that a transmitting station does not overwhelm the receiving station with data, okay. Which means that the transmitting station is transmitting at a very fast rate, and the receiving station cannot receive it, or cannot sort of process it, its buffer overflows, etc. So, the receiving station gets overwhelmed, and some of the frames or some bits, etc., may get lost. So, this is what we want to avoid, which is the topic of flow control. The receiver typically allocates a data buffer of some maximum length. Okay, you do not have you cannot I mean, store an arbitrary amount of data on the receiving side. So, there will be a very finite, sometimes quite small buffer on the other side. And so, if the receiver cannot process it, sort of goes into the buffer, but then the since we have a small buffer, or you may have a limited size buffer, eventually the buffer would overflow, and this is what we want to avoid. So, after receiving data, the receiver must do a certain amount of processing before passing the data on to the higher level software meaning maybe the network layer. Now, this is an example why flow control is necessary. So, this data is sort of torrentially coming from the above, the receiving side has just got this much buffer is full, and then whatever is coming, they are simply discarded. There is no way to accommodate them. All right. So, one way of seeing this is a same stop and wait flow control. Just as we use stop and wait for error control, similarly the stop and wait can be used for flow control. It is the same thing. So, this is the simplest form of flow control. The source transmits a data frame. After receiving the frame, the destination indicates its willingness to accept another frame by sending back an ACK frame, acknowledging the frame it just receives. The source must wait until it receives the ACK frame before sending the next data frame. Works fine when a message is sent in a few large frames, as we have seen, but if you have a large number of frames to send, and then of course, what happens is that its efficiency becomes a factor, and then so this is not a very good situation for that case when we have to send a large amount of data or a large number of frames specifically. Often the source splits a large message and transmits it in many frames. So, buffer size of the receiver may be limited. Handling errors for smaller frames is cheaper, okay, because if you have a very large frame, I mean your error control will come into that, error correction, error detection will become a problem. And on a shared medium like LAN, large frame sizes are not desirable for various, you know that it has the switches have to handle that and all that is there. So, we sort of make a more general case of this stop and wait protocol by giving a finite amount of buffer. If you one way to look at stop and wait is that on the receiving side we have a buffer of size 1, all right. Now, if you have a larger buffer, then how to handle it? Of course, you have to have buffer. In this case, you have to have buffer on both sides. You have to have a buffer on the transmitter side, you have to have a buffer on the receiver side. So, in stop and wait flow control, if A is greater than 1, serious inefficiency result. Efficiency can be greatly improved by allowing multiple frames to be in transit at the same time. Okay, so suppose two stations A and B are connected by a full duplex link. The link is has arrows on both sides, which means that we take them to a full duplex because the message has to flow from A to B, the ACKs have to come from B to A. Station B allocates buffer space for n frames. Thus, B can accept n frames and A is allowed to send n frames without waiting for any acknowledgement. Okay. So, this is all right because on the receiving side we have n buffer locations. So, that I am assuming that each location can contain one full frame. So, as the data gets so n frames can be pumped in even if the receiver does not process any of them, but then at least they can be accommodated in the buffer. So, it will not overflow. So, the receiver the transmitter can also transmit n frames. But why does the transmitter require a buffer? Because if you remember that the frames which the transmitter has sent, they have to be stored in the transmitter side because it may have to be retransmitted. The retransmission may be due to some error, I mean the frame may get a lot of noise which cannot be corrected on the receiving end, that is one thing. So, you may get a negative acknowledgement, that is one thing. Secondly, the frame may get lost altogether. Thirdly, the acknowledgement, I mean this frame may have reached, but the sender would know that the frame has reached only after it gets the acknowledgement, and the acknowledgement which the receiver might have sent may have got lost, all right. So, till it gets an acknowledgement, the transmitter has to store the the frame which has already been sent. So, on the transmitter side also we require a buffer. If n frames are to be in transit, then the transmitter has to store all of them because any of them might have to be retransmitted. So, on the A can send n frames without waiting for any acknowledgement. Each frame is labeled with a sequence number to keep track of the frames which have been acknowledged, because now since more than one frame may be in transit, maybe the first frame has been lost, the second frame has reached. Now, the receiver somehow has to know that this is the second frame or the first frame has been lost. otherwise it will send an acknowledgement and the transmitter would think that the first frame has been acknowledged. So, you have to identify what is it that you are acknowledging in this particular case. So, you have to have a sequence number. So, and this sequence number, so the acknowledgement comes with the sequence number or some sort of small variation of it, so that the receiver sorry the transmitter knows what is it that is being acknowledged. So, B acknowledges a frame by sending an ACK that includes the sequence number of the next frame expected. This is what I mentioned as a slight variation. Instead of directly giving the acknowledging a particular frame, let us say frame number 53, instead of say it has got the frame number 53, but instead of sending ACK 53, it sends ACK 54. That means up before, I mean the 54 is the number sequence, next sequence number which is expected in the next frame. So, which means that up to 53 everything has been received. So, that is the small variation. So, instead of the sequence number of the next frame expected, this also explicitly announces that B is prepared to receive the next n frames. That means from let us say beginning with the number specified, which means suppose n was 10. So, when B is the receiver. So, when B gets the frame number 53, so the next frame it is expecting is really 54. So, it sends an ACK 54, and which also means that B must be having, let us say, this buffer size of 10. So, from 54 to 63 it is ready for all these packets. It is not ready for frame number 65, by the way. So, up to because its buffer size is only 10. So, so that is what it indicates. This scheme can be used to acknowledge multiple frames. B could receive frames 2, 3, 4, but withhold ACK until frame 4 has arrived. By returning an ACK with sequence number 5, B acknowledges frames 2, 3, 4 at one time, because so in this protocol when a particular frame is acknowledged, say frame number 53 is acknowledged indirectly by sending ACK 54, that means all frames up to 53 have been received. Okay. That is what this ACK 54 is saying, all frames up to sequence number 53 has been received. So, one particular ACK may act for a number of frames. So, this also has an advantage that if the ACK frame, if one of the ACK frames, suppose 3 was also acknowledged, 4 was also acknowledged, and the acknowledgement for 3 had for some reason it has sort of vanished, that means it got killed on the way. But say if the transmitter gets an ACK 4, it knows that means ACK 5 really, that is the acknowledgement for up to frame number 4, that means 2, 3, 4 everything has been received. So, now we come to this sliding of this window. The sender maintains a list of sequence numbers that it is allowed to send. This is the sender window. Receiver also maintains a list of sequence numbers that it is prepared to receive, that is the receiver window. So, the buffers on the two sides really, so they represent the two windows. So, on the transmitter side, so these are the frames which the transmitter is allowed to send if transmitter has got all these frames from the higher layer, that is. So, but it can accommodate only that many frames now in its buffer. So, that many. So, that is the window of transmission, and the receiver also has a window that these are the frames which I am now ready to receive. Now, what the transmitter might do is that transmitter might transmit some of these frames and they may be in transit. The receiver window will still be same, because receiver still has not got them. Now, as it gets them one by one, the receiver window slides, and as the ACKs reach the sender, the transmitter's window slides. So, we have a sender window and we have a receiver window. Since the sequence number to be used occupies a field in the frame, it is clearly of bounded size. Okay. So, the sequence number to be used occupies a field in the frame. So, you cannot have arbitrarily long sequence numbers, all right. So, if the even if you are sending a very large number of frames, but then your sequence number will be bounded depending on how many bits you are using for this sequence number. So, for a k bit field, the range of sequence numbers is 0 through 2 to the power k minus 1, and frames are numbered modulo 2 to the power k naturally. So, now the numbers will the frame numbers are going to repeat because of this bounded size of k. So, the frame numbers is going to repeat. So, if k equal to 3, that means after sequence number 7 you have to go back to sequence number 0. Okay. So, the next slide shows a depiction of the sliding window for a 3 bit sequence number. The actual window size need not be the maximum possible size for a given sequence number length, it could be less actually. So, for a 3 bit sequence number, a window size of 4 can be configured. If two stations exchange data, each need to maintain 2 windows. To save communication capacity, a technique called piggybacking is used. So, this is the case we are talking about when both sides are trying to communicate. I mean previously also both sides were communicating in the sense that the so called receiver was sending an ACK. Okay. Now, let us say suppose it is a two-way communication which is going on. Now, we need a pair of buffer locations, that is a pair of windows on both sides. Okay. So, we want two sets of buffers on this side for the two windows, and the two sets of buffer on the other side for the two windows. On each side we will have a one receiver window and a one sender window. And in this particular case, another thing we can do is that you can piggyback the acknowledgements. So, you need not send an acknowledgement frame by itself. Okay. So, this is piggybacking. Each data frame includes a field that holds the sequence number of that frame plus a field that holds the sequence number used for acknowledgement. If a station has an ACK, but no data to send, it sends a separate ACK frame. So, if the communication is only one sided, that means one transmitter and one receiver, so the receiver only sends an ACK frame, but if the communication is from both sides, what they can do is that for the communication, that is message from here to here, its corresponding ACK piggybacks on the messages or the actual frames which are going from this side to this side. So, you need not send an acknowledgement frame by itself, which is of course saving a lot of time, because if you remember, you just remember the simple case in stop and wait, the acknowledgement was travelling all alone, but for that took its all its t prop, that is the propagation time. So, but all that is saved because you are using it for sending real data. So, that way piggybacking is nice. Of course, you must remember that if the if it is sending some message, say if you are using piggybacking and if you are sending some packet and you do not have anything to acknowledge, but still you will have to put in something on those bits. Okay. Otherwise, those bits will have some values anyway. Okay. It cannot be blank, it can be each of the bit will be either 0 or 1. So, it may be misinterpreted on the other side. So, something will have to be sent. Anyway, that is a small technical point. So, this is what the picture is looks like for sliding window. So, you have on the one side. So, these are the frames which are to be sent 0, 1, 2, 3, 4, 5, 6, 7, assuming only 3 bits for the sequence number. So, again the numbering starts 0, 1, 2, 3, 4. This 0th frame and this 0th frame, they are really two frames, two different frames. And this is from this is the frames which have already been received. So, 7, 0, 1, 2, 3, 4, etc. So, these are the frames which have already been received. So, if the frames have already been received, what happens is that up to 3, suppose the this frame has been acknowledged. So, the unacknowledged first unacknowledged frame is here, and your window is suppose you have a window size of let us say 4 or 5. Okay. So, 1, 2, 3, 4, 5. So, up to this is your window size. Once he sends the acknowledgement, this window will slide, and once he gets an acknowledgement of 4, then his window will slide. So, this is the general scene. Now, there are some variations about this acknowledgements that we can do, and we will discuss that. These variations just to make it try to make it a bit more efficient. So, we will just look at couple of variations now. One is go back n ARQ. So, this is once again based on the same basic sliding window protocol, which is most commonly used. A station may send a series of frames sequentially numbered modulo some maximum value as usual. The number of unacknowledged frames outstanding is determined by window size using the sliding window flow control technique. This is once again as usual. Now, while no error occurs, the destination will acknowledge incoming frames as usual, okay, using receive ready or RR frames. If the destination detects a frame error or it receives a frame out of order, it sends a negative acknowledgement for that frame. So, it sends a NAC or negative acknowledgement using reject or REJ frame. So, it sends a negative acknowledgement for a particular frame if it is received badly. So, previously we were only sending ACK or not sending anything at all. Now, if you have got an erroneous frame, we send a negative acknowledgement for that. And go back n means that negative acknowledgement in this sending the negative the particular frame may have been may have come in as faulty. So, that was a negative acknowledgement for that was sent. Now, what the sender will have to do is that the sender will have to go back to this particular frame and retransmit from that frame onwards all the other frames which it might already have transmitted. Okay. So, that is the go back n. So, the destination will discard the frame in error and all future frames until the frame in error is correctly received. So, the destination does not, even if it has got a sort of erroneous frame and it might have got a couple of frames or more frames later frames which may have come in, but they are not sort of acknowledged or I mean they are sort of discarded, because until and unless the erroneous frame is correctly received, it will not move. So, the source station on receiving a REJ, that is a reject, must retransmit the frame, that particular frame which was sort of which went in an erroneous form, plus all succeeding frames. Okay, that is the go back n, all succeeding frames. So, let us just quickly look at the window size limit for go back n ARQ. For a k bit sequence number field, the maximum window size must be limited to 2 to the power k minus 1. Suppose that the data now why is it that the window size cannot be greater than 2 to the power k minus 1? This is the reason. Suppose that data are being exchanged in both directions. Station B must send piggybacked acknowledgements to station A's frames in the data frames being transmitted by B. This is required even if the ACK has already been sent, since B must put some number in the ACK field. This we have already discussed. Assuming a 3-bit sequence number, suppose that a station sends frame 0 and gets back an RR1. That means from 1 onwards. So, from 1 onwards it has to send back all the frames. So, 1, 2, 3, 4, 5, 6, 7, 0, all this it has to send and gets another RR1. Okay. So, this might either mean that RR1 is a cumulative ACK for all 8 frames received correctly, or all 8 frames were damaged and the receiver is repeating its previous RR1. Okay. A repeater, a receiver might might have to repeat the previous acknowledgements because it has to put something in that acknowledged field. So, this problem can be solved if the maximum window size is kept at 7. Okay. So that they will not go overflow into the next set of sequence numbers. So, they will not they will never overflow. That is why the sequence number has to be I mean the window size has to be kept smaller than this 2 to the power k minus 1. If you make a very large window size, there will be a number of packets here or frames here with the same number. So, if you get an acknowledgement or a negative acknowledgement, you will not know which frame it is that is being talked about. Okay, it is as simple as that. Now, this I mean people try to improve on this, because if you remember that in go back n, when you get a negative acknowledgement, you have to go back to that frame, that transmitter has to go back to that frame, send that frame again and send all succeeding frames again, although it might have transmitted them once, and actually what might have happened is that the receiver might have received them also in correct order, but since the receiver is not moving and the transmitter has to retransmit all that, and the frames which were received correctly received earlier, they are rejected. Okay. In order to address this, what people then thought was to allow selective reject. That means, this particular one is rejected, maybe some subsequent frames are accepted. So, here the only frames retransmitted are those that receive a negative acknowledgement, in this case called selective reject, that is SREJ, or that timeout. Of course, if acknowledgement does not come and it times out, it has to be sent again, because the frame might have been lost altogether, but otherwise only those which get a negative, specific negative acknowledgement, only those specific frames are sent again. So, this would naturally be more efficient than go back n. Receiver requires storage buffers to contain out of order frames until the frame in error is correctly received. So, if a particular frame is wrongly received and then some subsequent frames are correctly received, now they are have to be stored in the buffer, so that when this wrongly received frame is retransmitted by the transmitter and it comes in a proper shape over here, it has to be inserted at the I mean in the middle of that list somewhere, all right. So, you have to maintain that. So, receiver must also have the appropriate logic circuitry. So, if it all that is if this inserting into the this buffer management and the inserting into the buffer and taking out of the buffer, etc., if that is being done by hardware, then you have to have the logic circuit for putting things inside the list somewhere. Similarly, for the transmission side, it may have got all these frames lined up which have already been transmitted. Out of that, one of them gets a negative reject. So, instead of the one at the head of the queue, so to say, I mean something from the middle may have to be taken out and retransmitted. So, the transmitter must also have that capacity. So, the receiver must also have the appropriate logic circuitry needed for reinstating the frames in the correct order. And transmitter is more complex, because it must be capable of sending frames out of sequence. Receiver is also slightly more complex, transmitter is also slightly more complex. Another drawback is that the maximum window size can be no more than half the range of sequence numbers. Okay. This is another, this is a small problem with selective reject. Now, previously you remember it was up to 2 to the power k minus 1. Okay. Now, we can use only half of that, not the full thing. We will see why. Assume 3-bit sequence numbers as in the previous example and a window size of 7. Consider the following scenario. Station A sends frames 0 through 6, because we have a window size of 7. So, we can send frames numbered from 0 through 6 to station B. B receives all 7 frames and cumulatively acknowledges with RR7. Okay. So, it has received, and the next one it is expecting is the 7th one. RR7 unfortunately gets lost in transit. Station A times out and retransmits frame 0, because it has not got any of the acknowledgements, because all these for 0 through 6, all these acknowledgement was clubbed together and one RR7 was sent, which unfortunately got lost in transit. So, but station A has not got any acknowledgement. So, it is holding all these original 0 through 6 frames in its buffer. So, now it times out and retransmits frame 0. B has already advanced its received window to receive frames 7, 0, 1, 2, 3, 4, 5. Now, B wrongly assumes that the frame 7 has been lost and that this is a new frame 0 and accept. So, this 0 which B interpret, which was actually the old frame 0, is interpreted as the new 0 number frame by B, and it assumes that 7 has been lost in transit. So, maybe later on a negative acknowledgement or reject for selective reject for 7 would be sent, but this 0 now the frame has now got out of order. So, problem arose due to overlap between sending and receiving windows. For k bit sequence numbers, maximum window size therefore has to be smaller. Go back N and selective reject. So, these are the sort of diagram for the two. We already know what these are. So, this is the go back N. So, acknowledgement, then the frame number 2, which is actually the third frame, came in an erroneous fashion, error was detected and a negative acknowledgement was sent. All right. Once the negative acknowledgement is sent, although 3, 4, 5 had been sent and maybe they have been reaching over here, but this has not moved, this window over here has not moved beyond 1. So, it sends 2 again, and all these 3, 4, this 3, 4 mind you is being sent again over here 2, 3, 4. So, these are discarded on the receiver side, although they were correctly received, and this is 0, 1, then 2, 3, 4, 5, etc. This way it goes. All right. Now, over here what happens? So, this is what happens. So, this was the go back N scheme, and in the selective reject scheme, so 0, 1 was received as usual, and the third frame, frame number 2 came in erroneous. So, a negative acknowledgement or NAC 2 was sent. So, when it gets a NAC 2, 2 will be retransmitted, but 3, 4 has already been received correctly, and acknowledgement of 3 and acknowledgement of 4 has also reached the transmitter. So, the sender will now send number frame number 5, frame number 6 and so on. So, please note the difference here, it has to send this 2, 3, 4 again, here this 3, 4 need not be sent again, 2 of course have to be sent again because it was negative specifically rejected, but then you can go on with 5, 6 etc. Okay. So, that is why this one is slightly more efficient than go back N. So, this is another picture how the I mean we have gone through this before, so how the Windows slides. So, what happened is that so this was the window 0, 1, 2 have been sent, and as 0, 1, 2 have been sent, the receiver window has slid, and then so it has ACK 2, after 0, 1 it sends an ACK 2 and then it gets 2 also. 3, suppose 3 was lost. Okay. So, although it might have received 4, 5 after that, they are discarded in go back N. And when there is a selective reject, the difference is that suppose the frame number 3 was got lost on the way, 5, 4 that is 4 and 5 which have come in over here are buffered, so that when you get back a 3, you can plug 3 in its proper position and the window can slide very quickly on the receiver side. And maximum window size we have already discussed, this is going to be 2 to the power k minus 1 in case of go back. Okay, so now we have discussed some of the major techniques which are used in the data link layer. So, what we will do now is that we will look at just one more protocol. Okay. This is a somewhat general version of we have already discussed PPP, that is the point to point protocol, which is used for just what it says, point to point communication. But there could be a point to multi point communication also. For this we have this high level data link control, this is the name of the protocol. Okay. So, this is the name of the protocol, or HDLC in short. just okay. I mean, this is not so high level any longer, it is not considered so high level any longer, but even then anyway. So, but this is an important protocol. So, there are some variations of this which are used in various places. So, we will just look at some generic way how this HDLC is done. So, this is an important data link protocol. This HDLC or some variant of this is widely used. It also is the basis for many other important data link control protocols. Okay. So, so this I mean the formulation of this protocol envisages 3 types of station. One could be primary station. These are responsible for the operation of the link. That means primary station is in some sense it is something like a master, all right. So, this will for setting up of the link etc., and for all some other control purposes etc., and the primary station holds the key responsibility for that. So, there is some kind of a master. It may not be only one master, that we will come to that later on, but a primary station is the one who will initiate the setting up of connections etc. So, we will see that. So, this is responsible for operation of the link. Frames issued by primary station are called commands. So, primary station gives command. And then we have secondary station, it operates under the control of primary station. Frames issued are called responses, just as the frames issued by the primary station are called commands and the frames issued by the secondary stations are called responses. Primary maintains a separate logical link with each secondary. As I said that this need not only be point to point, this could be a point to multi point communication also. That means there is one primary station, maybe a number of secondary stations. So, the primary is communicating maybe with each of them maybe on the same medium. So, if that is so, then the actually the primary is maintaining a virtual link with each of the secondary. So, it will maintain its own data etc., for each of these virtual connection. This the primary station has to do. Secondary station is of course under one primary. So, this multi point business does not come into picture on the secondary side. And then we may have combined station. It combines the features of primary and secondary. So, in that case it may issue both commands and responses, and combined stations actually are very common. And then there can be 2 types of link configurations. Unbalanced configuration consists of one primary and one or more secondary stations. So, if you have one primary and maybe one secondary station, so this is more like a point to point link. If you have one primary and a number of secondary stations, then it is more like a point to multi point link. Okay. An example of a point to multi point link could be, suppose you have a server and a number of terminals which are all hanging on the same cable, and maybe the server is polling. So, in this case the server would be the primary station and these terminals would be all secondary stations. They are communicating only with the primary station, which is the server, and the server maintains a virtual link with each of them. The terminals or the secondary stations just maintain the link with the primary station. So, this is an unbalanced configuration. So, one primary and one or more secondary stations. In a balanced configuration, this consists of 2 combined stations. Okay. That means a combined station, if you remember, is the station which can be act both as a primary station as well as a secondary station. So, so in a balanced link on both sides we have combined stations. So, both of them can act as primary as well as a secondary. Now, 3 data transfer modes. Okay. One is normal response mode, which is in that unbalanced case used with unbalanced configuration. Primary may initiate data transfer to a secondary. Primary, so as I mentioned before, that it is the responsibility of the primary station to initiate data transfers. A secondary may only transmit data in response to a command from primary. So, this is the normal response mode used with unbalanced configuration. all right. So, this is one case. Then we can have asynchronous balanced mode ABM used with balanced configuration. So, either combined station may initiate transmission. So, in this case it is as I said that since this is on a balanced configuration, that means on both sides of the link we have both two combined stations. So, both of them can act as primary and secondary, and either combined. So, since both of them are combined stations, any of them can initiate the transmission and the transmission can start. So, this is ABM, and the other is ARM, asynchronous response mode, used with an unbalanced configuration. Here the secondary may initiate transmission, primary still retains responsibility for the line initialization, error control, etc., that is done by the primary ARM. This is not very common. Sorry. So, the NRM is used on multi-drop lines. For example, a number of terminals connected to a host computer, the computer polls each terminal for the input, just the example I talked about earlier. So, this is used on multi-drop lines. Also used on, it could also be used on point to point links. If the link connects a peripheral, let us say a terminal, to the computer. So, if it is a point to point link and you see what is happening is that one of them is primary, the computer side, that is the primary station, and the peripheral side is the secondary station. So, NRM in all these unbalanced cases, the NRM may be used. Okay. Then ABM, this is the, as I said, this is the most widely used. On both sides you have combined stations, makes most efficient use of a full duplex point to point link, as there are no polling overheads. You do not have to do any polling, since this is point to point. ARM is rarely used, may be used in very special situations where a secondary may need to initiate transmission. Now, let us look at the there are different types of HDLC frames. Okay, different types of HDLC frames. So, so we will look at some of these different types of frames. One type of frame is called an information frame, which contains user data. Then piggybacked acts, that means the next frame expected. So, when you are piggybacking, that means you remember that on actual data some acknowledgement is also going, and this acknowledgement is telling you about which is the next frame to expect. Poll or final, this is a command or response. Supervisory frames, flow and error control. Now, go back in and selective reject. So both these are possible, and then there is a frame which says that this is the final one, no more data to send. Then there can be some unnumbered frames which are used for control purpose. We will see an example later on. Some mode setting commands and responses, information transfer commands and responses, recovery commands and responses, miscellaneous commands and responses. By the way, you do not have to remember all these because when you are trying to use it or design it for some particular situation, you can always look up the reference and see what exactly the different frames are, what are their formats, etc., etc. What I am trying to do is that I am trying to give you a flavor of the kind of information which this for a protocol, a typical protocol would need to exchange, okay, and some typical ways in which these protocols work. Okay. So, this is an example of HDLC operation. You have say from this for this line setup from the primary station, you send an SABM. SABM stands for set asynchronous balanced mode. So, he is the initiator. And so he want to send an ABM kind of a set ABM. So, on the other side it sets an ABM. Maybe what has happened is that after some time this SABM was not acknowledged. So, it times out and sends an SABM again. Now, it gets a response back UA. this is an unnumbered, there are some unnumbered frame, you remember. So, this is an unnumbered acknowledgement. Okay. And then after some time there will be, I mean after this of course possibly there will be some transfer of data etc., and then there is a disconnect frame which is DISC, which is going from here. Now on the other hand, you may get frames like RR and RNR. Okay. RR stands for receiver ready and RNR for receiver not ready. So, they if you look at the right hand side, there are some RR and RNR, receiver ready, it sends a receiver not ready. So, these are going back and forth, and in between there may be two-way data exchange, an actual data which is being exchanged through these I frames. Okay. I is for information. So, these information frames. So, a lot of really link setup and ACK and all this is traveling on both sides. From the reject, there is has to be a recovery, since suppose it is using a selective reject. So, reject 4 is going on this side, then I40 is coming from the other side, that means 4 is now being retransmitted. I40 you note had been transmitted before, it got lost on the way, so a reject 4 had come. So, I40, so the same that selective reject is working over here. Similarly, timeout recovery, that means after some time say I30 was sent and was never received. So, then after some time it timed out. So, it says that you have to some recovery frame is required. So, this RR and receiver ready frame it sends, and it sends receiver ready, then I30 was transmitted again. So, these are the basically typical kind of transactions which are going on between the two stations. Once again, as I said, that this gives you some idea about how these data link protocols etc. they work and how they do error and flow control etc. Okay. And finally, just a quick look at the various fields. Once again, you need not remember all the details, but some of the, I mean once again to get the flavor, there are some flag fields. Each frame starts and ends with the special bit pattern. This how do you know that for the framing purpose? So, this is a special pattern which is used for start and end. Of course, if you use a special pattern in order to accommodate this pattern within the data itself, so you have to do bit stuffing is used to unambiguously identify the flag fields. Of course, when you do bit stuffing, this is not 100% reliable, you must remember. When the same flag is used to mark both the beginning and the end, a 1 bit error may merge two frames into one. Okay. A 1 bit error in the, let us say ending pattern. So now that will not be interpreted as an end of frame pattern by the receiving side. So, the two frames may get merged. Similarly, 1 bit error inside the frame could split it into two. So, all these things may happen. This is not 100% correct, but by bit stuffing would work most of the time. Then there is some address field. So, it identifies the secondary station transmitted. If you remember, it is not used for or not needed for point to point links, but is included for the sake of uniformity. For point to multi point links, naturally you need to have the address, because when the primary station is sending something, it is addressed to some particular secondary stations out of all the secondary stations which are connected to it. Both single octet, that is a single byte, or multi octet or multi byte addressing are possible. Then there are some control fields, define 3 types of frames. Information frames carry the data, flow and error control information, also piggybacked using ARQ, and then some supervisory frames are there, and then some unnumbered frames are there, provide supplemental link control functions. So, I and S frames use 3-bit sequence numbers, and the information field present only in I frames and some U frames can contain any sequence of bits multiple of 8, but is usually limited in length from consideration of error control. Frames with empty I field are transmitted continuously on the idle point to point lines in order to keep the connection alive. And finally, some frame check and sequence fields. So, with this example, we now come to the end of this general data link control, but still we have seen some examples of data link control. For example, we have seen some examples of MAC. like with token bus, token ring, etc., etc. We will see other examples of MAC as we take up other kinds of networks. Similarly, we have seen some kind of error and data control. By the way, the similar approach is used in some other higher layers also. We will talk about it when we come to it, and we will talk about some more specific and more widely used systems from the next class onwards. So in the next class, what we will do is that we will look at one other type of communication and how MAC is done on that in satellite communication. So that will be the next topic. Thank you.